Okay, let's get started. So I've posted PSET 5 now, so you should get started on that. This homework is meant to be a lot easier than the other ones, so hopefully it actually is. So there was a good discussion on Piazza about the second question on PSET 5. So are there any questions about this one, about this automata stack automaton? I really should have put a Pimp My Ride meme in there somewhere. Automata, stack automata. I put it in a stacking, okay, whatever. But are there any questions about this and how it works?
I think I'm pretty good enough. Thank you.
So everyone understands how this works, right? What this main transition means. No. So what do you think it means just by looking at it?
It's a go-to?
It's like a go-to, yeah. So note, how many final states are in this thing? Exactly one. So this transition says, okay, if I take this transition going to Q1, then if I want to take this transition labeled with main on it, then I will start a new stack frame. So when I first start up this thing, I have a stack which corresponds to which module that I'm actually in. So the first time I start up this thing, I haven't entered any other one, so I'm just in this one module main. Then if I take this transition 0, and then I take this transition main, then I'm going to put another main on this stack, and that's going to start a new stack frame as if I just started in Q0 brand new. But, so if I look at the input 0, 1, this first transition on the first stack frame, I've read that 0 and it's gone. But when I start this new stack frame, I start from where I was when reading the input before. So I still have a 1 to read. So in the second stack frame, what I do is I take this epsilon transition over to Q3. So when that happens, there's and the NFA says, yeah, I'm done with this stack frame, then this second instance of this stack frame goes away. So I basically pop this off the stack, and then I re-enter the stack frame I was in before. And when I do that, I'm in this state Q2, the end of the transition. So in some sense, if we take this diagram, copy it, paste, and then make it smaller, then it's as if I have these two superimposed, like Q0 is mapped to where Q1 is, and Q3 is mapped to where Q2 is. Okay, so it's like if I in the second one, if I enter Q3 and stop, then I'm going to resume computation in the original stack frame in the end of that transition Q2. And so when I'm in Q2, I still have them in the first stack frame. I read this final, I read this final 1 to go to Q3, which means I read that 1. I go to Q3, and I say the NFA stops the computation, so I pop that one off the stack too. I've read the input, and I have nothing in my stack now, so therefore I accept the input. Okay, is that clear how that works? Yeah.
Why do you take that epsilon transition on the second stack?
I don't have to. So here I'm showing a way for 0, 1 to be accepted. But there may be some other convoluted path that leads me to that final state as well, and I could take that one as well. It's an NFA, essentially, but now I have these transitions, which are the module names, and I can instantaneously jump to another instance of that module, and then computation there, and then when that one ends, I come back and resume from where I was before. Okay? Hopefully that makes, yeah.
Is our start state still the first Q0, or is it a smaller?
So it depends on which stack frame you're in. So if in the first one I'm in Q0, then I read that 0 go to Q1. I'm making another instance of the whole module itself. So in the second stack frame, I technically am in Q0, but is as if I was in Q1 in the original stack frame. It's like I'm copying and pasting the entire machine between the two states of that one transition, that main transition. Yeah.
So the two instances in this example of main that are on the stack, they have no knowledge of each other.
Good, correct, yeah. So you only know the top stack frame that you're in.
Okay, so if they can't share information, what is this machine actually capable of doing?
Well, certainly at least the regular languages, right? Because I don't have to have the module names on the transitions. So what do you think the parts in the problem set are having you try to show? It shows that every language recognized by this thing is a context-free language, and every context-free language is recognized by one of these things. So what would that show? It shows both directions, which shows equality with the, killing me here, the context-free languages. So what do we know so far recognizes the context-free languages? By definition, the grammars that we've been working with. So what do you think the two main parts of that question are having you try to show? That we can convert from an arbitrary one of these things to a context-free grammar, and from an arbitrary context-free grammar to one of these things. Let me ask you. So, what is the language of this machine? It's actually stated in the question, but oops. So, what's the language of this machine? Yeah, 0 to the n, 1 to the n, right? What's the grammar for 0 to the n, 1 to the n? Here's one.
0s.
Yeah, 0s1 or empty. How many rules are in this grammar? 2. How many paths are there from Q0 to the one final state? 2. Do you think that's a coincidence? It might be. So maybe you can probably think about that a little more. Okay, so it's showing equality with making a CFG from one of these things and the other way around. Okay, any other questions about this? So I made this homework a little easier because there's a test coming up. So when's the test? Wednesday. So I think I'm not going to talk about the entire thing today because it's not made yet, but I'll talk a little bit about it. So how many points is it out of for the option A people? 200. 200 points. But I'm going to offer 240 points. So 240 possible. So it's going to be 6 questions, 40 each. And so, and of course, if you happen to get more, you carry those along with you. And it replaces midterm 1 if you did better on this one. And then other great thing about it is it's mostly going to be about the conversions and maybe some decidability results about regular languages or something like that. So it's going to be not only an easier test, but it's going to have more points available, so it should be better for you. And it replaced the midterm 1 if you did better. So hopefully that's good. Yeah. And another thing, it only covers material through whatever we do Friday. So it won't cover Monday. Okay. Any questions about the test? I'll probably like show the test like I did before on Friday or Monday.
Lecture after? Or no?
Yeah, there'll be a lecture after.
Oh.
Actually, I don't know. We'll see how far we get. We'll see. Any other questions? Yeah.
Not on the exam. I've got the question on P4.
Okay. P4.
I'm having a hard time parsing what's happening in question 5.
So.
It's the odd stutter.
Oh, odd stutter. Okay. Okay. So what is the... Okay, I'm going to have to make another page here. Add page. Sweet. Okay, so oddstutter, or oddstud, or whatever. Okay, so what is the question saying that you should show?
That if odd stutter is regular, then, or if the length is regular, then odd stutter.
Okay, so L regular, then that implies oddstud L regular. A great thing about these questions is once you understand what the question is asking, then it actually can make the question a lot easier. So what does L regular mean? There's a DFA for it. So let's say D for L, so some DFA D. And if I make a DFA for oddstud L, are we done? Yeah, because that would show that it's regular, right? Because we have to show it's regular. Could I also make an NFA?
Yeah.
Yeah. Could I make a regex?
Yes.
That's interesting. Regex. Well, so you can do this with any one of those, or regular grammar if you'd like. But if I do it with any one of those models, then this is all I need. So if I show you a way to look at this DFA D, or if you want to think regex for L, and you modify it in such a way that you get oddstud L, then that'll work. Well, if you have a general procedure to look at each part of the DFA and say, okay, if I see this, then I do this, then we're done, right? Okay. Well, think about a transition. So it's actually a lot easier for regexes, so I won't give a hint for that. But if we have a transition like this in the NFA, or the DFA for L, could I simulate? So remember, a lot of these questions are about simulation. So could I simulate from this state to this state oddstud of a single character? So what would be a way to do that? Yeah, we can just add a new state that's never been used before, because if it's used before, then I might do something else that is unintended. So how can I do that? So if I have these two states as before, how can I simulate reading a positive odd integer number of A's? So that would be that's something you have to think about. Okay, but we can simulate it with extra states. So if we see a transition like this, then we simulate it between these two states by adding this extra new state and then simulating it with these extra transitions, which corresponds to, because think about the oddstud of L for a single string. If you look at a single character of that string, it'll be in the oddstud of that string a positive odd integer number of times, regardless of what the rest of the string is, right? So if I have A, B, A, and then I repeat the first A to have it be 3 times instead of once, that choice was made independently of the rest of the string. So remember, in a DFA, the transition is taken independent of what the rest of the string is, right? So that's why we can actually do some kind of simulation in here to simulate a positive odd integer number of times I've read that one character. Okay, does that make sense?
Yeah.
It's actually a lot easier with regexes, but I intended it to be done with DFA or NFA.
You can show that you can convert the D for L into a D for oddstud of L?
Or an NFA or whatever, yeah.
You've shown that implication?
Yeah, because I just look at every transition and I modify it in such a way, then I must get the oddstud of L. So if I apply this procedure to every transition, then I'm done. And I make sure if I use new states in here, that I never use that state in any other case, because then I may do something unintended. Other questions about answer your question?
Yeah.
Okay. Any other? Yeah.
If the input output is contain more than A, B, C also, like C, D, it can be contain anything, right?
It can be what?
Like if you do a DFA for only two alphabets, like A, B, or
No, it can be an arbitrary alphabet.
you take any two, like A, B.
Well, you can't assume what the input alphabet size is.
Okay, but then how can we draw a DFA?
Well, you don't have to draw it. You can just say, if you see a transition which happens to be this character, or any character, for each character, look at a transition that corresponds to that character, and then modify it accordingly.
You don't need to draw it with this or write it.
Yeah, as I said, apply it to each transition. Yeah. What is the it in that sentence?
Say if you have A, B,
Hmm.
then if you have the alphabet be like A, B, A,
It has to be positive integer number of times in that one place. So for that reason, you can actually, based on that reason, you can show it for regexes quite easily, because it's only locally on that one character that you need to worry about it. Other questions? Okay. So what were we talking about at the end of last time? It's on the screen. Yeah, Chomsky normal form. So what was the reasoning behind studying Chomsky normal form? Good question. So the main idea was that when we had this grammar for balanced curly brackets, something that was unintended was we made this long string and that with a whole bunch of variables in it, and then all of them went to empty, which was kind of annoying. What we kind of want to happen is when I apply a rule, I get some more of the string and then some more of the string, instead of doing a lot of work to get a long string and then I finally get what I want by applying even more rules than what I intended. So that was the main idea. But another consequence is the grammar is a lot simpler in structure, because if we insist that every rule be one of these three types, then it's either the case that you make two variables with one variable, or a single terminal, or only the start variable makes empty. So because of this, we can't have that situation where we have a long string and then a whole bunch of variables just collapse the string by going to empty. So anytime I apply a rule like this, I make more variables. Because these right-hand side, these two variables are not the start variable, they cannot possibly go away, which means that each one of them must make something of the final string. And so therefore, the number of rules I need to apply is actually a lot fewer than maybe if the grammar was not in Chomsky normal form. So what we started to look at was, well, we had this grammar for balanced parentheses, which is, balanced curly brackets, which is here. But then we realized, oh, the start variable is on the right-hand side of the rule, and of course we can't have that. So we fixed that by making a new start variable s0 and going to that original start variable, and so we solved that problem immediately. The good thing about this is that it eliminates that problem, and now I can focus on applying the other things that this grammar does not satisfy for Chomsky normal form. And one of them is this rule right here, for instance, which is where one non-start variable makes the empty string, and of course Chomsky normal form can't do that. So we fix that by saying, let's look at these things called nullable variables. So what's a nullable variable? Right, it either makes epsilon directly, or it makes only variables on the right-hand side where each of them is nullable. So there is some way for this variable to make the empty string. And what we wanted to have is that we don't want that to happen. We want to simulate as if that occurred. So if S, for example, makes empty string, I want to simulate everywhere else in the grammar, either S makes the empty string or it does not make the empty string. So then I add additional rules to handle that case. So that's what we did here. We looked at, say, this rule right here. There are two S's on the right-hand side. So either or both of them could make empty because we found S is nullable. So then we added additional rules for each of the cases that might happen. So either this first S may go to empty and the other one does not go empty, which is simulated by this rule, or the other case where the second one goes to empty and the first one does not, which is simulated by this rule, and then the other case when both of them do. And then we look at all the possibilities, account for all of them, and then we finally say, yeah, we had this S to epsilon here, but we've simulated it everywhere else. We don't need it anymore. So then we finally get rid of it. Okay? Any questions about the first two steps? Okay, and we also found that both steps don't change the language of the grammar, which is vitally important. Because in the first case, we just graphed on S0 goes to S at the beginning of any derivation. And in the second case, if we ever applied some variable goes to empty, we simulated it with a different rule. And so therefore, we don't change the language. Okay, well, let's look at the grammar we have so far now. Is it in Chomsky normal form? No, and how can you tell? Two variables, right. So this first one seems not quite what we want, right? It has one variable makes exactly one variable. And this is kind of annoying because if we have a bunch of these types of rules where we just make one variable, essentially we're just going through the grammar not ever doing anything, right? We're just replacing this variable with another variable repeatedly until maybe we make something. So these things where one variable makes another one are called unit rules. So step 3 then is try to eliminate, quote unquote, unit rules. So as a reminder, unit rules are of this type, where you have one variable makes exactly one variable. Okay, so let's copy down our grammar. Forget what it is. Okay, so we want to eliminate unit rules. In this case, how could I eliminate that unit rule? Well, let's see. Is there another unit rule anywhere else in the grammar? No, there's no other unit rule. Could I use that? Probably. Well, what if I copied and pasted all of these rules up to S0 directly? Well, the rules I copy up, none of them are unit rules. And if I replace that S0 goes to S with these 4 rules, do I have any unit rules left? No. Well, think about it. If I applied this rule, then that means I'm eventually going to apply one of these rules. S goes to something else. Well, I'm just going to directly go to one of those cases. But think about this situation. So I'm going to do it in a different color to indicate that this is not what we have right now. What if we had this? So we have a unit rule upstairs, and then A makes S, and S makes A. Well, it's not quite as easy now, right? So I could try to copy and paste, well, actually this would work, but I could try to copy and paste those 5 rules for S upstairs and downstairs for the S0 and the A variable. But if I have a long grammar, then this copying and pasting could be quite difficult. So how do we handle this in the general way? So put your CSE310 hat on, so we're going to be talking about directed graphs for a little bit. So the way that we handle these is, notice, if we could potentially apply either S0 goes to S, or S0 goes to A, or S0 goes to S, which makes A eventually, or S makes A eventually. So there are many ways we could apply unit rules, or even A goes to S, right? So there are many ways we could apply unit rules. So what we're going to do is we're going to make a directed graph where each of the variables is a vertex. So in this modified example, not the original, the modified example, how many vertices will I have? How many variables are there? 3. So I'm going to have 3 vertices of my directed graph. So S0 is going to be a vertex, S is going to be a vertex, A is going to be a vertex. And what we're going to do is, if one of these vertices has a unit rule with some other vertex, I'm going to make a directed edge between them. So here, S0 goes to S, that means I'm going to put an edge there. S0 goes to A directly, so I'm going to make a directed edge there. Let's see. S makes A directly, so I'm going to add an edge there. And A makes S, so I'm going to put a directed edge there. So this is, and that accounts for every unit rule in this directed graph. And what are we going to do? We're going to look at every single one of these actually, that's not quite right. What we're going to do is, if some path a directed path exists between any 2 vertices in this directed graph, so this means directed path. So if A and B are just arbitrary vertices in this thing, and I have a directed path from one to the other, then I'm going to do this copying and pasting thing. So for instance, in the S0 goes to S thing, that's a directed path. It's one directed path. And now what I'm going to do is I'm going to copy the rules of S that are not unit rules up to where S0 makes S. And then I see, okay, well, I see S0 makes A in this graph. Then I'm going to make the rules that are not unit rules involving A, and I'm going to copy them up as well. And what we're going to do is, suppose we had something else like this, where we had some other vertex. And we had a unit rule S makes B. So this is just an example. So what we're going to do in addition is, if there's a path between them, I'm going to add directed edges that weren't there. So we see that there is a path from S0 to B. So what's the path? Yeah, so S0 goes to, or S in this case, you can do. S0 goes to S, and then S makes B. So now I'm going to add the edge, S0 goes to B. So I'm going to add the edge there. So if there's a path, I'm going to add edges as necessary. And then once I'm done adding all those edges, then I do the copy and paste between the variables. Does that make sense? Most of the grammars that you're going to be working with are not going to be too complicated in this sense, but we need a general purpose algorithm to do this. Could a computer compute this graph for you? Yeah, so in fact you can actually have an algorithm to compute this graph, and then therefore you can have a computer do the copying and pasting of rules. So let's actually work with the unmodified grammar. So I'm going to fix the grammar from before. So in this case, this original grammar we have so far, how many vertices am I going to have? 2, right? Because there are only 2 variables. So therefore, I can only have two vertices. So what are the edges that I'm going to put in this graph? Well, there's only one unit rule, so I'm going to only add one edge to this thing, so which is S0 goes to S. Right? There's no S to S0. Yeah, go ahead.
Can you explain why S doesn't have unit rules in it?
Because it just happened to not have any. In a general grammar, it could have unit rules, but in this case, it just happened to not have them.
So, in the transition where it's, for example, open brace S, close brace, why is that not a unit rule?
Because it's two terminals. If it's a single variable, then it would be a unit rule.
So if you have any number of terminals and a variable, that's
Yeah, that's not a unit rule. So remember, the unit rule form is one variable makes one variable, and nothing else. Yeah. If there's terminals, then we can't say anything because that's not a really unit rule anymore, because I'm actually making something of the string. Other questions? Okay, so we see one directed edge here. So what should I do by looking at this one directed edge graph? Yeah, copy the non-unit rules of S, which there are no unit rules, so that's good, and just copy them up to where the unit rule is, and then delete the unit rule. So here, I'm going to do S first, and you'll see why in a second. So S0 can make empty, but I don't feel like writing all four of those rules again. And it's the exact same four rules above. So there's actually a shorthand you can do. So you can do OR and then do this. Just say, these rules are directly the same up here. I copied them over and it's exactly the same. So it's to help you avoid having typos there. So it's the exact same rules above. But any questions on how we did that? Did I change the language when I did this? No, why not? Suppose if the derivation does not use a unit rule at all, did I modify any of those rules in this one step? No, I didn't change any of those. But suppose I actually did use a unit rule. Well, what we did here is we simulated that one unit rule with all of the rules that it could make. So all the rules that involve S on the left-hand side, we simulated by putting all those rules directly where the unit rule was. Okay? So it's all just simulation here. So in fact, I don't change the language of the grammar here, which is good. And the good thing is I don't reintroduce start variable on the right side, and I don't introduce epsilon rules because I already dealt with those. Any questions on this third step? Yeah.
If you were to write them there, the ORs, there's no like order you have to go through. You pick any one of those.
Yeah, so I can, because it's just shorthand for multiple rules, and the order of the rules does not matter. Okay. Other questions? Cool. Is this grammar in Chomsky normal form? No, so how can you tell? Yeah, more importantly, there are terminals and variables and mix on the right-hand side, and we can't have that. So luckily, these last two steps are really, really easy. So we're done with the hard steps. The last two steps are easy. So step 4, so if you read the Sipser book, the Sipser combines these last two steps into one. I prefer to split them up because it's easier to visualize how everything is going to work. So the way that we're going to try to eliminate this mixture or long right-hand side pattern is we're going to first make sure that either the right-hand side is just a single terminal or all variables. Okay, so it's either one terminal or possibly many variables. Could I have one variable on the right-hand side? No, what was step 3 all about? Eliminating unit roles. So I can't have one thing on the right. Could I have two things on the right side? Two variables on the right side? Yeah, certainly. Could I have 3 variables on the right-hand side for Chomsky normal form? No. So that's what the last step is going to all be about taking a long right-hand side and breaking it up. So step 4 is going to be ensure right-hand side is single terminal or all variables. And of course, the start variable makes epsilon, but that's just a special case. Okay. Well, I have these mixtures of variables and terminals, but what do? I want to have all variables on the right-hand side. Oh, sorry? What if I just made a single variable for every terminal, had that variable for that terminal, make only that terminal, and replace every occurrence above with that variable? Would that work? Well, I didn't violate anything for CNF about one variable makes one terminal. That's okay. And if I put it upstairs where the grammar is, the original grammar, then I'm just going to have all variables on the right-hand side. And so therefore, I'm okay. So let's see. So what are the terminals in this grammar? The left and the right bracket. So I'm going to need to have 2 new variables here. So I'm going to make u sub right bracket make that single right bracket. So this u sub right bracket, that is just one variable to indicate, yeah, this thing only makes right bracket and nothing else. And then, of course, I'm going to make a left one for left. And then in the grammar upstairs, of course, the rules for S0 are going to be almost identical to S, so let's do S. Okay, so what we're going to have here is u sub left bracket S, u sub right bracket S, or u sub left bracket, u sub right S, or u sub left S, u sub right, u sub S, u sub right. And then, of course, S0 is just epsilon or the rest of it. Yeah.
If it was more the rest of it, how would the S's be defined if you were to just copy that into S0? There would be no S's then.
No, it's still S. Yeah.
Like, when you write that, you mean that whole thing is right there, right?
It's literally the same.
Yeah, so then wouldn't it be S0, epsilon, or all of that, and then even looking for S's, it wouldn't know where the S is because...
What do you mean S wouldn't know where S is? I'm not sure what you were trying to say.
I guess maybe if you were to write the longhand that way, you'd be able to see.
I love notability.
So like that, how are the S's defined there? Because then I'm imagining
The whole grammar is one big structure. It knows what the variables are. So when I see this S right here,
yeah.
It says, look, if you're going to apply a rule that has S on the left-hand side. Okay, so like in the original grammar. So it's the same story here. How does S know which rule to apply?
It just looks at S right there.
Yeah, it just looks at the rules corresponding to S
Okay.
on the left side. Yeah. Any other questions? Yeah.
So we've introduced too many variables. I assume we're taking care of that in step 5.
Correct. Yeah, we'll deal with that in step 5. But any questions about this one thing? I'm going to put it back to where it was. Okay. So it doesn't clog up. Okay. So as was just mentioned, is this in CNF? No. And how do you know? More than 2 variables on the right-hand side. So we need to break up long right-hand sides. So let's just work with the S rules and then work our way to the longer ones. Should I fix that rule, the one on the right? The use of left, use of right? Why should I not fix that one? Because Chomsky normal form says one variable makes two variables, A-okay. So I'm not going to touch that one. What about this one? Yeah, I'm going to need to fix that one. So how can I fix that one? And stay within the rules of CNF and not introduce problems we had before.
Make a state that goes to those two states.
Ah, that's a good idea. So let's see. Let's look at that one thing. I get too excited about this type of thing. But anyway, that's a great suggestion. What if we just looked at, say, those first two? You could look at the last two if you'd like, but let's say the first two. Let's have a brand new variable make exactly those two variables. So let's say, so S is making this thing. So let's convert this to say, okay, S is going to make some variable. Let's call it x1. So a brand new variable with use of a right on the end. And then what is x1 going to make? It's going to make u sub left s. So u sub left s. We actually kind of saw this when I first introduced context-free grammars, where you force part of one rule into another. So what happens here? If I want to apply this rule, then I need to apply something with x1 on the left-hand side. And then x1 is going to be such that this is the only rule that x1 will ever make, which means I must apply u sub left s, which means I'm simulating the original rule. Okay? And then, okay, well, what about, so that handles this one. The other one, let's see, how would I handle that one? Almost exactly the same, but I can't use x1 anymore because that, what x1 makes is not the same thing here. So what can I do instead? Well, let's look at these first two. Let's have it make x2s, where x2 makes u left, u right. Okay? So that handles most of them, but what about this really long one? So I'm going to copy it down. So there are actually multiple ways I can handle this, but what's one way I can handle it? Right, so I shouldn't use new variables every time, but it doesn't violate correctness if I reuse variables I made last time. I better not add a rule for x1 because then that'll change things. But if I see these two variables used somewhere else and I want to use a variable for it, x1 is a valid candidate for that. So in fact, if we have it make x1 for those first two and then x3 for the last ones, so x3 makes u right s, then that'll work. And we do the exact same thing for the S0 rules. Okay, well, does this actually change the language? Well, let's check. If we didn't use one of those long right-hand side rules, did I change those rules? The ones that are the right length and not long ones? No, I didn't ever touch those. So suppose I did use one of them. Say this one. Well, we deleted it and added these. Where is it? We added these two rules, which force it to carry out the exact same computation that the original, same derivation that the original did. Because we forced x1 to only have one rule with it. So it can only make one thing, and so which corresponds to the original rule. And so therefore, I don't change the language because I can get one derivation from the other and vice versa. Okay? Are there any questions about this? Yeah.
So you can get kind of clever choosing your x's to reduce the number of new rules you might have, new variables you would have to create.
You could, but technically what you should do is you make a new variable every single time. So what would happen is that a lot of new variables make the exact same thing. But for correctness reasons, that should be what you do, but it won't be wrong if you use the same variable multiple times. What would be wrong is if you had x1 make something else, right? Because then if I wanted to apply use of left s, and then I can apply something else, that'll change things. But if you don't do that and you just reuse the same variable, that's okay. And that actually does save a lot of work in some cases. Any other questions? Yeah.
Could you remind me in step 4
Mm-hmm.
why we bring all those rules up instead of just writing S in the or statement?
Because it's exactly the same and it's just to save time and sanity.
Can we write S in where you can?
Well, I mean, I could literally copy them up and if you wanted.
Or just mixing up how we're using the arrows.
I'm not sure what your question is.
In the line for S0,
Mm-hmm.
turn it into epsilon or
Or-
rules.
Or any one of those 4 rules, yes.
Can we just write S since we have a line that's mapping S?
But so should I put, so great question. So ignore this, just put S there. Should I do that? No, why not? Because that's a unit rule. And we eliminated unit rules. So that was the main reason for that. Other questions? Yeah.
When you copy it up there, you keep the rule below it as well.
Yeah. I'm never gonna. When I do the copy and pasting, I don't eliminate the rules before. Yeah, because I may apply these and I can recursively go through S again, and so I don't want to change that. And yeah, if I deleted the rules before say the S rules, then S can't make anything, and so that would actually change the language. So yeah, you better not delete the ones before. Just copy it over. Don't cut it over. Other questions? Oh, look at the final. Well, I don't have the final grammar here, but did we just achieve Chomsky normal form? Yeah, because think about it. The long right-hand sides are not there anymore. I have exactly 2 variables. I can't have 1 variable because we've already eliminated those. Step 5 doesn't introduce unit rules again. I don't have the start variable, non-start variable making the empty string because we fixed that before and we never reintroduced it. And we never have the start variable on the right-hand side because we fixed that earlier and we never reintroduced it. So in fact, we can actually convert any context-free grammar into CNF. So the upshot of all this is every CFG can be converted into CNF. Yeah.
So in step 5, we have to break it down into 2 variables?
Yeah, you have, because that's what Chomsky normal form says. Mm-hmm. The reason for 2 will be evident when we talk about languages that are not context-free. But we can't get away with 1, because if I just did that, then I'm just replacing that 1 variable with another one, and I can't get anything longer than 1 character. So that's why we have 2 variables there. And that's actually going to lead into the next thing, unless there are questions. Yeah.
So do grammar parsers usually convert to
Mhm.
this form before they do their work?
Exactly. Because we're going to talk about the acceptance problem for CFGs next, and so therefore it'd be a lot easier when talking about the grammar in CNF. So the algorithm we're going to talk about next is not practical. It's just to show that it's decidable. But what the real compilers do is an algorithm called, you probably have heard of it, called the CYK algorithm, and named after the authors. And what this algorithm does is it's a dynamic programming approach based on the grammar when it's in Chomsky normal form. So it exploits the fact that it's in CNF to actually parse whether the grammar can make that string really quickly. Whereas if it's not in CNF, then it could take a lot longer to actually even figure that out. Other questions, though, before we do that? Yeah.
Would you mind reminding me what a unit rule is?
Yeah, so unit rule, I wrote it here. So unit rule is a rule where it has exactly one variable on the right-hand side and nothing else. So essentially, if you apply that rule, you're replacing that variable on the left with the variable on the right. So in a sense, that rule is completely useless to the grammar.
Except for epsilon.
What do you mean epsilon?
You kept epsilon?
You-
Oh, that's not
Yeah, it's nothing to do with a unit rule. It's a variable making another variable. But other questions? Yeah.
So we didn't really show the full grammar in Step 5, correct?
Mhm. Mm-hmm.
So,
But it's the exact same thing as before, but we make these 3 substitutions everywhere, and you're done. Mm-hmm. Any other questions? Okay, so we talked about this problem ATM for Turing machines. We showed it was undecidable. Then we talked about A sub DFA, and is that one decidable? Yeah, because we can just simulate the DFA and it always halts. What about the acceptance problem for grammars? So it's in the middle between DFA land and Turing machine land, so it could be decidable, it might not be decidable. So let's phrase this as ACFG. So it's almost exactly the same as the acceptance problem for DFAs, Turing machines, whatever you like. But here we have that G generates W. So this one better be decidable because your compiler better be able to parse whether your program is actually syntactically correct or not. So this basically is the reason why compilers exist, in some sense. Yeah.
What does it mean for grammar to be decidable? It will either make
Grammar is not decidable. So it depends on what language you're talking about. Is whether this language is decidable or the grammar's language is decidable. I'm asking. The language of the grammar or this ACFG? This ACFG? I'm giving you the grammar and an input, and you're tasked to figure out whether that grammar can make that string or not. So like way before when we talked about that one grammar, I forget what it is, but where we checked whether that one string can be made by that grammar just by doing this derivation. So the key is here, can you find the derivation that makes this string or not? And so, as you might expect, this problem is decidable. So before we get into the full details of it, let's take a little bit of a detour. So what was the thing we just converted? All CFGs can be converted into CNF, in Chomsky normal form, right? And one of the nice things about CNF is, suppose we had a rule like this, where we had one variable makes 2 variables. What is true of those 2 variables on the right? Well, they're not the start variables, so that's actually quite helpful. Could those variables go away?
They must be.
Right, they must be helpful in making something of the string. They might make one character or more, but through some other rules. But they must make something of the string. Well, suppose W is of length n. And suppose we have some derivation that can make this thing. Okay? How long could that derivation be? Or how long is that derivation? Well, let's see. What is one way we can make a derivation for w? So let's say w is equal to w1 through wn. It has n characters in it. Now I'm going to assume for the moment it's not empty, but it's just a special case. What's one way I can make this? Well, one way I can make it is, well, I got to start with the start variable always. Well, then what's going to happen is it either makes a one character directly, if w happens to be one character, but let's suppose it has more than one character. Then what we do is, okay, it's going to make two variables, and then maybe I apply something with b and that makes two variables. Then maybe something with one variable and that makes two variables. And then at some point I'm going to have some variables u1, u2 through un. And then one way I could get the string out is transform each one of these variables at the end, these n variables, into one of the characters. So in one rule application, maybe I can convert this u1 variable into that first character w1. So that would be one rule application. And then if I apply another, then I'm going to get two. Maybe I would do it for u2. That's another variable I can try. And then let's say u3. And then at some point, I'm going to have one more to go. Let's see. wn minus 1 un. And then finally, I make the entire thing. So that's one derivation for this string. And what you could do, of course, is you can work with the variables at the end in any order you want, right? Because it's a context-free grammar. Another way you can do it is, well, if you want to change the first variable to the first character at the beginning, that's one way you can do it before you get all n variables at the end. Well, could I get a shorter derivation than this? Well, at some point, I'm going to have to transform n variables into n terminals. Why? Because there's no rule in a grammar in CNF that makes two terminals. It can only make one terminal, right? So at some point, I'm going to have to transform n variables into n terminals. Well, how did I get to n variables? I started with 1, and how many did I add in order to get to n each time? I must have had to add n minus 1 variables to get from 1 to n. Well, how many can I add in a single step? 1. So the first time, so I must have n minus 1 rule applications to get up to n variables somewhere, and n more rule applications to transform those n variables to the n terminals of the string we're after. So how many is that in total? 2n minus 1. So in fact, I can't get a shorter derivation than that. So every string of length n can be derived in exactly 2n minus 1 rule applications. Nice. What about the empty string? What is 2 times 0 minus 1? Negative. So can I apply -1 rules to get the empty string? No. So what is it in that case? How many rules possibly would I need to have? 1. How do you know? Because s, the start variable, may or may not make the empty string, but there's no way to get back to the start variable. So in fact, that's one of the main reasons behind CNF. We can guarantee for any string how many rule applications it'll take to actually get there. So I think it's a good time to have a break, and then we'll come back to this.